Hi. Super excited to be here. I'm sure Ed is excited too. So please welcome Ed Shee. Did I say it correctly? I think
You did, yeah. Thank you. Yeah. So, hey everyone, I'm Ed Shee. I am head of developer relations at a company called Selden. So what I do is I look after our open source community. I kind of help improve the developer experience. Work on docs, create code samples, things like that, and generally help us build really awesome products. Right. That's probably enough, right? You didn't come to listen about me, right? You wanted to find out some cool stuff about deploying machine learning models. So let me just share my screen and then we'll get going. Okay, cool. So if I jump on here and maximize the screen, hopefully you can all see that all right. As I said, what we're going to cover today is deploying machine learning systems that scale, right? And I'm going to talk a little bit about where the AI landscape is at, and then we'll dive into some specifics in a minute. So in terms of an agenda, what we're going to run through is first we'll look at the MLOps landscape, explain a little bit about what even is meant by MLOps as well. I know that people have different definitions, and some of you may not have even heard of it. Then I'm going to talk about the data-centric AI movement. From there, I'm going to then talk about how the machine learning systems that we deploy are kind of changing from just collection of endpoints to these fully fledged systems. Then I'll give a live demo showing some of the benefits you can get from moving to a data flow architecture and so on. And then we'll wrap up at the end and do some Q&A. What you guys will get out of this, right? So the first thing is how machine learning deployments are changing. The second is that a data flow architecture is super important, and you'll find out why. And then you'll learn how to deploy these complex machine learning systems. So let's start at the beginning, right? I know this is a kind of DevOps audience, right? So some of you will be very familiar with machine learning and MLOps. Others of you may not have any experience at all, right? So let's start by looking at the machine learning lifecycle. Now, typically, when we want to create a machine learning model, there are a bunch of steps we go through. So the first thing we do is we gather some data. We can't train a system unless we have some data. But then the next step is to do some data engineering around that, right? It's kind of cleaning the rows, the columns, the empty values, the badly formatted stuff, etc., so that we've now got a nice clean data set. The thing is, at that point, we still don't have something that can be used to train a machine learning algorithm, right? What we need to do is a task called feature engineering, which converts that data into numerical values. That's because the way machine learning models work is everything is an input is a number and everything on the output is a number, right? It's all just mathematical operations under the covers. Finally, once we've done that, we can train a model. And then having done that, we're going to do some sort of model evaluation. How accurate is my model? How well does it do the task that I've trained it to do? Once we've done that, we go, okay, this is good enough. Let's try and deploy it. And then finally, once the deployment's up and running, it's about monitoring that consistently, making sure it's running, etc. A lot of these things will seem familiar from the kind of DevOps process we go through. The final thing is that this is a fully iterative process, right? As we deploy a machine learning model, and then we're doing live predictions, we're gaining more and more data. We want to be capturing that, feeding that into our data gathering process in order to redo the whole cycle and build better machine learning models. Now, this whole process, right, the ML lifecycle, I like to call the process of doing this machine learning engineering, and you'll see that term used quite a lot. But it's not MLOps, right? MLOps is basically taking this lifecycle and then adding automation, reproducibility, and infrastructure management over the top of it, right? With machine learning engineering as a technique or as a discipline, right? You might be your company might have hired a machine learning engineer, right? They can run through that life cycle because they have a great set of skills. But when you get to the point where you want to deploy 5, 50, 500 models, right? You don't want to have to hire 500 machine learning engineers to do that for every single model, right? And that's why it becomes about building this automated and reproducible infrastructure, so that a single data scientist or machine learning engineer can be way more productive. So that's what MLOps is and where we're at. Now, in terms of like what the landscape looks like right now in 2023, is that actually a lot of those individual stages are pretty well solved. So if we take the stages down the left-hand side, what I'll do on the right-hand side is I will map a bunch of primarily open source tools that you can use in each of those stages. So for data gathering, tools like Snorkel do a great job. Data engineering, people should be familiar with things like Spark and Airflow. Dagster being an open source framework you can use in there. Feature engineering, Feast is a very popular feature store that runs on Kubernetes. For model training, I'm sure a lot of you have heard of TensorFlow, PyTorch, but then other, there are smaller libraries like GBM, XGBoost, etc. Model evaluation, so this is checking how well the model performs. Things like MLflow, deep checks, again, a bunch of libraries that we have in this space. And then in terms of model deployment, there are things like Selden Core, ML Server, or NVIDIA's Triton Inference Server. Finally, for monitoring, we're looking at things like Alibi Explain and Alibi Detect. So as I said, each of these individual stages are pretty well solved now. The challenge is taking all of those, combining them together, and building a sort of integrated platform that allows you to reproduce all of these steps in a nice, uniform fashion. Now, on top of that, right, what we're also seeing in the general machine learning field is this rise of data-centric AI as a movement. Right now, what's all this about? Okay, so if we think about the way we did machine learning, typically what would happen is we would have some sort of data set. In a lot of cases, we would use like a public data set, and like the MNIST data set. If any of you follow machine learning, you've probably heard of that one. And then people would build different model architectures and evaluate them against these public data sets to see how well can I do. So what you're seeing here on the screen is this is just a screenshot from Kaggle, which is a website that runs data science competitions. And this kind of shows you exactly what's happening, right? There's a fixed data set, and data scientists or ML engineers compete to try and build the best model architecture that can handle that data set, right? And what you'll find is that, in this example, right, the top classification was able to get it right 76% of the time. And as we see, to be in the top 10, you needed to do above 72.2%, right? So these are pretty marginal gains for what is probably some very, very complex algorithms underneath and architecture in order to get that increase. So what's happened is loads of the research in AI has focused on building better architectures. But actually what we've seen over the last year or two is that if we focus on providing better data, the increase we can get in terms of things like accuracy are way, way higher than if we focus on just the model architecture. And so in this example, right, if we focused on getting better data, we might see that all of these architectures perform at like a 90+% accuracy score. Now, the reason I'm talking about this and the reason this is important is because this is spilling over into the machine learning deployment phase, right? So if we look at, again, a kind of simple traditional machine learning deployment, it was kind of, we deploy it as one big unit. We probably containerize the machine learning model and any of the code around it. And we provide inputs. So here on the left, we've got this kind of, inputs coming in, runs through the machine learning model, and I get a prediction out the other end. I don't really care what's happening in between. The problem is that as we move to a more data-centric AI world, right, we want to be able to take multiple sources of input. So if I give this example, which is this is very heavily based on Uber's implementation of how they predict driver allocation and price for journeys, right? If we look at all the different inputs here, we've got kind of the available drivers, driver requests, maps, real-time traffic, historical traffic data, weather data, spatial data, and temporal data. All of these kind of inputs are being fed into the system. And on the outputs, what we're getting is an allocated driver and a predicted price for that journey. right? Now, the problem with deploying it like this is that we just basically have a black box in there. And only the data scientist or the machine learning engineer who built the entire system understands what's going on inside. Now, why is this a problem? So let's take an example of drift, right? So one of the problems we have with machine learning models is that they are built to model very complex scenarios, right? Things that we can't just write if statements for, or a bunch of deterministic code. By nature of that, what that means is that these change over time. So, the example here, right? A city might decide to pedestrianize a road, or more drivers become available, right? All of these kind of things change the way that the system can work underneath. Or there's legislation brought in a city around how many drivers are allowed to be on the road. Those kind of things. Those are obvious changes, but there could be more subtle things in there as well, such as just people decide to walk more, right? If we as a population decide to walk more, how does this driver prediction model know that? And the answer is it doesn't. And we can do these machine learning monitoring techniques called drift detection to try and detect when this does happen. So to explain this a little bit better, I'll give you a very simple example. So imagine you've built a machine learning model that predicts house prices, right? So given a whole bunch of features, how many rooms it has, where it's located, whether it has a garden, the square footage of the house, etc., right? You can imagine that you've got hundreds of features. And with those, you can very accurately predict the price. Now, if I train that on a load of data that I've got now, it's not necessarily going to be the same in 3 months' time, right? If you take an example of the pandemic, right, immediately house prices changed dramatically. Flats in city centers became much less valuable, and larger houses in leafy suburbs became more valuable, because with everyone being locked down, people needed space to work at home. They wanted outdoor space to be able to hang out in without going out into public, and nobody needed to be in the city center anymore. So that's a situation where the underlying relationships of your model have changed, and you need to be alerted to it. So, looking back at this example, right, if I notice that we're getting fewer requests for drivers, right? What does that actually mean, right? It's very difficult to understand what that drift has done to my model, because it's all just like a black box, and I just have a bunch of inputs and a couple of outputs, right? So the way that we can solve this is to migrate to a data flow architecture, right? And I'll explain a little bit more about that in a second, and I'll show some in the demo. But what the benefits of a data flow architecture are is that now you have this complete data flow graph by design. And for those of you in the DevOps world, you can think of this a little bit like the kind of move from a massive monolith to a nicely distributed microservice model. That one of the differences here, though, is that whilst we have that decentralized, we can update components separately, scale things separately, we get all the benefits of like a microservice architecture. We design a data flow architecture to be naturally asynchronous, right? And this is really important for machine learning, because a lot of the workloads that we have are streaming workloads. If you think of things like object detection, I might be taking a video feed and streaming frames from the video through my system, right? I want to be able to handle that asynchronously. Another thing this does is it provides this data lineage and tracing across the whole system, so we can kind of understand the interactions between the components. And then finally, it allows us to do flexible experimentation. So if I want to replace a section of my my driver prediction algorithm, I can do that in a safe way by kind of A/B testing or shadowing traffic and things like that. So what this means, by having moved to a kind of data flow architecture, our system that did look like this now looks a lot more like this, right? Where we can kind of understand the internals of the system, we can change things separately, and we can see here, for example, that let's say we wanted to understand why the price, we've noticed drift on that, right? And what we might find is, by interrogating these inputs and outputs from all of the systems, that actually the key driver for that was that the weather has changed, and that maybe making assumptions here, but maybe when it's raining, more people request rides, and so the kind of weather changes and the driver requests change, and that's the biggest thing that's driving this price. Now, before we wouldn't have been able to know that. Okay, so why am I telling you all of this? So as I mentioned at the beginning, I work at a company called Selden. We actually have an open source framework called Selden Core, which we built to deploy and monitor machine learning models on Kubernetes. Right now, what we did last year was we totally rebuilt the entire framework on top of a data flow architecture. So now we can, rather than being a collection of single endpoints where your model is kind of containerized and deployed as a monolith with an API, right? We can now build these complex machine learning systems, which is what is being demanded now as people get further and further on in their adoption of AI at their company. So what is Selden Core, right? As I mentioned, it deploys and monitors models on Kubernetes and Docker Compose. So again, another thing we did was made it a bit more infrastructure agnostic. At the moment, Docker Compose and Kubernetes, but we may bring support for other things in the future. And then it creates these containerized microservices for your machine learning workloads with REST and gRPC interfaces, and then also defines these like powerful pipelines for routing and combining models and so on. There's a lot more it does, but I'm not here to kind of promote the library. I'm here to show you some cool examples and teach you how to build ML systems. The two things we do have to understand though for this demo to work is the first is the concept of a model. And this is basically like a single deployment unit within Selden Core. It could be a machine learning model. It could be a data transformer. It might be an explainer, etc. And then a pipeline, right? And a pipeline is a way to connect these models together and create this data flow over the top of them. Don't worry too much about the YAML you're seeing here. I'll explain some of this in a demo in a second. So let's jump into a demo. Just before I show you some of the code and run through the examples, let me set the scene. So what we're going to do in this one, a little bit less complicated than the driver prediction algorithm, but hopefully one you can still all understand, is that we're going to get, what we're going to do is run a speech to sentiment pipeline. So you can see down this left-hand side, we're going to basically take audio in, we're going to transcribe that into text. So we're going to use a machine learning model to turn it into text. And then we're going to feed that text into a sentiment analysis machine learning model that's going to tell us whether it's negative or positive. And then asynchronously, right? So that's our kind of base pipeline down the left-hand side here. And then asynchronously, what we're going to do is we're going to run an explanation for each of these prediction requests to understand, why did the model think that this text or what I said was positive or negative, right? And so hopefully, as I go through the demo, this will all make a bit of sense. Before I do, just a quick primer on explainers. So explainers are a machine learning technique to try and understand the inner workings of a machine learning model. So one of the challenges we have with particularly things like deep neural nets is that we don't actually know how they work, right? And you've all seen the hype around ChatGPT and GPT-4, and a lot of scaremongering about, oh, nobody knows how the system works, right? At a high level, we do, but in terms of what the individual weights account for, we actually don't, right? And what we can do is we can apply techniques that attempt to explain these. Now, one of these examples is one of these techniques, is the anchor technique. This is the one we're going to use in the example. And I'm showing it here for an image because it's a bit easier to visualize. But if you imagine, so this left-hand image, right, of the dog is what we sent for prediction. And then the result came back from the classifier that, yes, it thinks it's a beagle. Now, how do we explain why it thinks it's a beagle? Well, what we can do is we can break the image into segments and then superimpose them onto other images and then feed them back through the classifier, right? And understand, does it still think it's a beagle? And if it doesn't, then that part of the image was probably not super important. And if it does, then it probably was, right? And if we do this enough times with enough sections of the image, we can build up what we call an anchor. And so in the middle, you can see this anchor for the beagle. which is basically, a bit of face and a bit of back and neck and area and so on. And it turns out, if we superimpose this on the right-hand side onto a bunch of random images, still 90% of the time, the model will think it's a beagle. So we know that these sections of the image are really, really important to the classification, right? And that's one way to attempt to explain how the machine learning model works. So the reason I'm showing you that is that the demo itself has an explainer in, and we're going to use that anchor technique, this time for text. So same sort of thing, we anchor it around a word and see how does that word affect the output. So let me jump up here. Right, you've seen the pipeline already. First thing I'm going to do is just import a bunch of libraries. And then I'm not going to go into too much detail on all the code. I'm just going to kind of explain at high level. I'll share this afterwards, and people can run through it themselves if they want to see the example. The first one is just a simple, this function is for taking audio from my microphone and then running it through the model. The important thing here, though, is now let's look at some of these models. So I mentioned that model section. So let's look at this one that I've highlighted. We can see, this looks like a very simple Kubernetes manifest, right? In fact, that's what it is. And we have a bunch of CRDs that run on your kube cluster. And I'm going to create this kind model, give it a name, and then I give it the storage location of my machine learning model. And what it's going to do is go and grab that and pull it down. And then I also give it requirements. So in this case, this is using Hugging Face, which is a machine learning library. But there might be other requirements in there. You want Python and TensorFlow and so on, right? And by that, it's going to schedule it on the appropriate servers. So I have two models here. There's this first one, which is Whisper, which is an open source speech to text model. And then I have this sentiment model as well. And then what I can do is I can then load those using this Selden model load command. And that's going to load it onto my cluster. What I'm going to do then is just check, are they available, and wait for it. And they're actually already up and running, which is great. So it's happened quickly. Okay, the next thing I'm going to do is create that explain pipeline. So I've deployed these two models, but I haven't kind of wrapped them in the data flow architecture yet. So to create the explain pipeline, we're going to do a couple of different things. I'm not going to show you all the Python code, but these first two are essentially input and output transformers. What they do is they take some data as it comes into the explainer, and they translate it into a format that the explanation algorithm is comfortable with, right? So this one is the input transformer, and then the output transformer down here, which looks very similar, is doing the same. It's taking the output from the explainer and converting it into a format that the rest of the pipeline wants to deal with. So those are kind of simple Python code that we can embed in this. And then if we look at the actual models here, we see the same sort of thing. So we've got this input transformer and then the output transformer, and we're giving them the storage location of the model. And you'll see, the requirements are slightly different for this. So I need Python, and I'm going to run this on ML Server, which is another open source framework. Cool. And then I'm going to load those models and just check that they're running. Okay. Now, the other thing I mentioned were, so we've now deployed these models. The second thing I mentioned were these pipelines, right? So a pipeline being a kind of collection of models, a bit like a DAG of how the data will flow through your system. If you look at this, what I'm defining here, so let me highlight this again so you can see what's going on. You can see I'm defining kind pipeline in here. Again, my name is just kind of sentiment explain. And then the key thing here within a pipeline is that I set a bunch of steps and provide inputs for each of those steps. And that's how I build up this kind of logic of where the data is going to flow through the machine learning system. So I'm going to create, for example, the first step will be sentiment. So it feeds it through the sentiment model. And then there's this kind of sentiment output transform, which is going to take this sentiment as an input. What that means is this model is going to take kind of output from this one, read it into this model. And one of the other cool things I can do is I can do these kind of tensor maps where I kind of translate the data from one format into another, etc. in between, so that this second model has things named appropriately for itself. The final thing I'm then going to do is define an output on the pipeline, which in this case, I'm saying what I want is the sentiment output transform to be the output of that. Okay, so I'm going to load that pipeline and just wait for it to run. Okay, all good. We can see model ready true down at the bottom. And then I'm going to do the same for an explainer model. So again, I won't dig into the YAML too much, but essentially what I'm doing here is deploying that explainer model. And this will take a little bit longer. It's a bit more of a heavyweight model. And you can see one of the nuances here is that for an explainer, I provide this kind of type in here, as well as a reference to which pipeline I want it to run in order to do those explanations. If that doesn't make much sense, what I think I'll do is jump back to here and remind you that so the way this explainer algorithm works is it superimposes things onto, for example, in this case, superimposes some sections of an image onto another one, and then feeds those through the machine learning system in order to detect like what changed. Now, to do that, obviously, we have to make lots and lots of requests to the machine learning model. So whereas down the left-hand side, we might have just made a single prediction with a single image, an explanation requires lots and lots of predictions to be done in order to come up with some sort of logic around how that explanation was made. So that's what I'm saying here, basically, is for that explainer, I want you to reference this pipeline, and this is the one you're going to use to make all those extra predictions in order to explain what's going on. Okay, that's all running. Finally, what I can do is then build this kind of speech to sentiment pipeline. This is a little bit more complicated, but essentially it's the same thing that you've seen back here, right on the left-hand side, which is this speech to sentiment pipeline here, where I'm saying, okay, take the prediction requests, feed them to this Whisper model, then to the sentiment model, and then put them out, but then also asynchronously send it to the sentiment explainer. And that's what we can see here, right? We can see the input, it first goes to the Whisper model, then it goes to sentiment model, which has inputs Whisper. And then after that, we send it to this sentiment explainer, right? And then the outputs, we're actually going to capture the outputs of both the sentiment and the Whisper model. Okay, so let's load that one and then check if that's running. Okay, finally, now the fun bit, right? We can actually test this out and see one of these systems running live. So let me record something. I don't know. I'm going to be overwhelmingly positive, right? And hopefully it will pick this up correctly. So this conference is absolutely fantastic. I'm really enjoying it. Okay, I don't know if you can hear the playback from there, but that's basically just a recording of what I just said. And now, having done that, I can run this inference, and you can see. So here's the text that it came back with. Actually, that was pretty quick. It's created the transcription from my audio. So this conference is absolutely fantastic. I'm really enjoying it. Okay, so it's got all of that right, which is really good. And then it's also run sentiment analysis over that text. And you can see it's positive, and it's like massively overwhelmingly positive. It's like 99.9% sure that this was a positive thing that I'd said. Now, what's really cool is we can then go and run this explainer and see. You'll notice that because that explanation runs asynchronously in the background, right? This one has already finished, and I can go and retrieve it. But actually, if I run another example, maybe, and then I get to this bit quickly, I can wait until that asynchronous pipeline has finished in order to get my explanation. So remember that the audio I fed in was, this conference is absolutely fantastic. I'm really enjoying it. And what the explanation has come back with is that the anchor for that is the word enjoying. So whilst, there's absolutely fantastic would be really positive, it's found that the word enjoying is the most indicative of the fact that this is a positive sentence that I've said. Okay, finally, having done that, what I can do is I'm just going to clean up and remove some of those models. Worth mentioning as well, all of this I can see from, if I go like model list, I can see all my models within here, and there's a nice CLI that you can interact with. If you're running this on top of Kubernetes, you can interact with it fully with the kubectl command line as well, right? And you can check all the pods underneath and so on. You can, one of the nice things is that we expose a lot of the Kubernetes API underneath. So if you want to be able to do, resource limits and so on, you can do all of that. Cool. So, right, let's clean that one up. And then what I'll do is I'll jump back into my slides. Okay, so to wrap up right from this, so the first thing is that data-centric approaches are improving the results in ML, and not just a bit, but drastically. Right, it's now been shown that improving the data for both training a model, but particularly for at inference time, right, can improve things by like orders of magnitude above an architectural change, which is what historically researchers had focused on. Having designed, come up with this data-centric approach, and with people shifting towards that in the way they build machine learning things, what's happening is the workloads are becoming way more complex, right? And you saw that with the example of, the kind of Uber driver prediction algorithm. The more data you take in, particularly from external sources or enriching it, the more complex the whole thing becomes, and it's no longer just a single input-output system. You have this full kind of architecture that needs to be deployed. Moving to a data flow architecture is needed, right, to deal with these complex systems, but particularly as we look at the monitoring and explainability aspects of that, right? Had I deployed that example, so if I just jump back here, and this example just as a single unit, I wouldn't have been able to do this explain sentiment step, right? Because what would have happened was I'd have sent audio to it, and I would have just got back a, positive or negative, right? And if I go, well, why is it positive? And I try and run an explainer across it, I can't, because I'm feeding audio in but getting text out, right? And then it becomes really difficult, So one of the nice things about moving to this data flow architecture is that I can do the original models where I take the audio, turn it into text, then I can feed it into an asynchronous pipeline to do explanations, right? And then I can return that to the user. And this is the kind of power of what you get out of this. And then finally, Selden Core is an open source framework that we've totally rewritten in this data flow architecture in order to be able to manage these kind of complex ML deployments. Runs on top of Kubernetes and on Docker Compose, and hopefully other things in the future. The final thing to mention is that we have a research paper that's been published on a lot of this, on kind of the move to data-centric inference and why data flow architectures help deal with a lot of the challenges that come from these complex ML deployments. So do go and give that a read. A lot of the work that we've done at Selden, we do in collaboration with Cambridge University, some fantastic researchers there, and yeah, it kind of reiterates in a lot more academic rigor what I have told you today. So with that, I kind of thank you all for listening, and you can reach out to me on, I guess this is probably reverse order of preference. So Twitter last, then email second, and then LinkedIn is probably my favorite. So do that one first. Maybe I'll reorder them in future, or I'll just check if you're actually listening when I say reverse order. But yeah, you can reach out to me on any of those. Thank you very much, and hopefully you'll be able to deploy awesome ML systems in the future.
Yeah, so thank you so much for your time. It was super interesting. I don't see any questions yet, but this just means that I allow myself to ask the first question, if I may. So I wanted to ask, like, what happens if you don't start from scratch? Like you talked a lot about like how you can start from this or that, but what if you don't start from scratch? Like, what if I want to deploy to an existing cluster? How do I do that? Is it too much to do? Is it possible? I'm sure it's possible, but like how? What would be the way to do that?
Yeah, great question. Right, I didn't really talk about the architecture underneath. So the way that we built these data flow streams are on top of Kafka, and the reason we chose Kafka was obviously it gives us like that very robust pub sub type system, but also Kafka streams allows us to do a lot of the things that you need to do with machine learning pipelines, like inner and outer joins and so on. Right, you end up with these. One of the things machine learning that happens a lot in machine learning is you have like multiple models and then you combine the outputs into another, or you split them off and run them to, you have
To have
one.
Kafka in between,
Yeah. So
in between the stages, you mean?
yeah, exactly. Right. And so Kafka, basically every single one of those models in a pipeline has its own input and output topic, right? Which just allows us to do all the mapping.
Right.
Well, back to your question, right? How does this work with existing setups? Well, the great thing is you can just point a Seldon Core installation to your existing Kafka broker, and it will just communicate with that one. So if you already have a Kafka running in your kube cluster, or you're using a managed service for Kafka, you can do that, right? And that is one of the nice parts. The other thing is that you can totally namespace the entire installation. So again, if you've got an existing cluster that you run all your workloads on, you can either create a new namespace or have a namespace that you want to restrict it to. It'll all run in there as well. And again, one of the neatest things I think about building a kind of a cloud native tool on top of Kubernetes is just that ecosystem of other tools, right? So, if you want to trace all of the requests that have gone through your system, right? We have integrations to Open Tracing and Jaeger and things like that, right? So, yeah, that I think is probably the biggest benefit. That ecosystem of other tools. Being able to send metrics to Prometheus and use things like Grafana to create nice dashboards of what's going on.
Right. I mean, it is crucial to have eyes inside your system, or else, like, how would you know where to look or what to look at? And sometimes just the logs are not enough. Sometimes you need a broader view. Oh, and now I see that we even got a question, so I'll read it to you, and I'll also bring it over here so everyone can hear it. So we have a question from Paul. He says, you mentioned that the explainers can be a bit heavy since they're making many requests to the ML. How big exactly is the performance trade-off? For which kind of MLs would you recommend it then? For which ones you wouldn't recommend it?
Mm-hmm.
Good question.
Good question again. The answer to that is, so there are kind of two questions there. The first is, how big exactly is the performance trade-off? It depends heavily on what the type of explainer is. And this is where explainability ends up being this whole field, right, that you can explore. But there are fundamentally kind of two ways you look at it. There's either this global view, so I want to create an explanation of how does the model as a whole make predictions, right? And that kind of thing you can run more or less like you can just run it once, and it's very computationally heavy because it has to look across the entire statistical data set and run lots of different examples. But then you get this kind of result which gives you a good kind of surrogate explanation of how the model works. Then the second type is a local explanation, which is what you saw in this, which is how is a single prediction, how do we get to that answer? And the answer might be very different for one prediction than it is for the next. Now, in those scenarios, they tend to be not quite so computationally heavy because you only need to do subtle changes around the features at that local level. And then so that's kind of much less computationally heavy. Depending on whether you would do it for every prediction, sort of depends on the use case, right? So we work with an insurance company who do it for everything because they find it's really, really important to be able to understand, if we flag something because we think it's a fraudulent claim, we want to know exactly why we flagged it as a fraudulent claim because it saves the fraud investigator time, which ultimately costs them more money than it would in terms of the infrastructure costs. Equally, if you were approving a mortgage, something like very high value, the infrastructure costs are absolutely negligible. But if in my example, you're just doing like a kind of audio with sentiment type thing, maybe it would make sense to do explainers on demand. So as they're requested by either users or by, in some cases, it might be an auditor who comes in and says, can you provide an explanation for why that prediction was made?
And that would be like way cheaper than having that not on demand. Like,
Yeah, yeah, correct. I mean, it also sort of depends on the model as well. So like, you know, a large neural network running image classification is going to require a lot more compute resources than a very lightweight tabular model. That for those you can run an explainer on everything pretty much, and it's still the inference cost is pretty negligible.
Mm.
And actually you can have it do real-time explanations as well, because a lot of them return in kind of sub-millisecond times.
Okay, that sounds good. All right. Well, so I want to thank you and again say that it was very interesting to listen to everything that you shared with us. And I don't see that we have any more questions. Is there anything else you would like to add before we say goodbye?
No, I think that's all. I mean, if you're interested in this, check us out on GitHub. Make sure you ping me and just give some feedback. Right, we're always looking for more feedback in building better frameworks that everyone can use. So yeah, thank you for your time, and thanks for hosting. It's been really good fun.
For sure. Okay. Bye.
Bye.
This is all we got. Remember the revolution in our minds. This is all we got.
Lock me out of this life institution. I am angry and high on illusions. Yes, I hate, but it's not a solution. Try my best, but I'm just a human.